And I usually keep forgetting because of the 40-minute issue with Zoom, with my current Zoom. So please remind me each time we log in for me to remind me to record. All right, so we'll continue. For others, it's beginning, but I'll still give you, I think you've probably seen the material, the two from metallurgy. I hope I've sent you emails with a thread of our past two lectures. So I hope you have
Yes, yes.
you've seen that. So I will be mixing our lectures will be a mixture of recorded sessions as well as live sessions.
Okay.
Recorded sessions as well as
Hello?
yes. So there'll be live sessions as well as recorded sessions. I know that
Okay.
others prefer to have them recorded throughout, but I think for the sake of questions and for me to know which areas are not clear, I feel it's just fair enough for me to have some of these lectures live sessions so that you're able to ask me questions there and then. I will try to record where I can. So just asking you to remind me. So anyway, let's go straight into our lecture for today. The structure of crystalline solids.
Doc, is
Yes.
there a way you can assist me?
Pardon?
On Tuesdays, I have two classes. Tuesdays at the moment, I'm split. The other side, the phone is on another lesson.
You're
See if
supposed to
I
be in
can
another
get
class?
it. Yes. So I was wondering if there's a way that you can assist. Maybe if this one can be pushed to either Monday or Wednesday, because on these other days I still have some other classes.
Okay.
On Wednesdays we have law. Like most of us have law. We are taking law. Those who are doing purchasing and supply.
Yeah, I meant Thursday actually. I meant Monday or Thursday. Sorry.
I can't get you clearly. So you're saying that you are busy now?
Yes, I'm in another class at the moment.
Okay. You should have told me this prior to this lecture. I was going to postpone it.
I tried to get to communicate on the LMS, but unfortunately I couldn't get. I wasn't successful. I never got any response from you.
Oh no, I wasn't on the LMS today.
Okay.
Or even a call would have actually helped.
Unfortunately, I don't have your number.
So you're saying that, so who else is having a class now?
I think. Let me check. Those that I was with last year.
Or maybe let me ask, who's having a class with Stephen now? So it's just you, Stephen?
It seems so.
All right, then I can excuse you, then we can continue. Then I'll just send the link to the recorded.
Okay.
Yes, we'll be excused. Okay, so we continue. So looking at the structure, so well, like I said, we're looking at crystallography, isn't it? But there's also what is known as metallography, okay, which we also look at. So under metallography, we look at the microstructure, the grain size, the shape, okay, of the solids, the phases that are present, phase proportions that are present. We look at the evidence also of heat treatment as well as cold working. While under crystallography, that's where we now look at the crystal structure of metals. And then we look at the types of the crystal structures. There's what is known as the FCC, face-centered cubic. There's the BCC, body-centered cubic. and HCP, that is the hexagonal close-packed Miller indices. Oh, sorry, close-packed, and then there's the Miller indices and the calculation of plane spacing. So this is what we're going to look at, okay, on the right side for this lecture. We're going to look at these also, but we are concentrating on what's on the right side for today, okay? So we looked at atoms in our last lecture, and we looked at the structure of atoms. So we know what atoms are made of. We will not go there. Going forth, for this lecture, we're going to look at atoms as a whole and their arrangements. So crystals, what are crystals? These are objects in which atoms or molecules are arranged in a periodic manner. You'll see that. I think I have enough illustrations with that. And what else do we know about materials and crystal structures? Materials which do not have a crystal structure are called amorphous or non-crystalline. So I'm sure we all know what crystals are. The simplest crystal we know of is which one? Which is a simple crystal we know for materials? Eunice, in your kitchen.
No?
I was saying, which crystals I was asking which crystals?
Salt.
Yes, salt is a common crystal. Which other one?
Sugar.
Sugar. Those are the most common household crystals that we find in our homes. Yes. So atoms in a given material arrange themselves in a pattern, and these arrangements, so the arrangements of these patterns and their patterns are the subject of our discussion. So we're basically looking at the patterns, and in particular the crystal patterns for us today. So we detail out the 3 common crystal structures in metals. We're going to look at them, and also we're going to consider the crystallographic points, directions, and planes. We'll also see those as we go. So that's the packing depends on the energy levels. So for non-dense random packing, you have that illustration there. The typical neighbor bond energy, you see, remember what we looked at last time when we looked at the energy levels, the equilibrium state, when the energy is at its lowest here, and then there's the state that looks like it's the equilibrium, but it's not. That's where our point here is lying. Kindly mute your mics, please. I think we remember this from last time, from last lecture. Those that can remember, we looked at something like this. Okay, so then we have the dense or ordered packing, where the atoms are very closely packed, isn't it? Like we see here in the illustration. So what's with the energy? The energy at its lowest, eh? Typical neighbor bond energy is there at the lowest point. Okay, more or less what we're calling the equilibrium last time. So dense ordered packed structures tend to have lower energies and thus are more stable. Okay, so the dense materials have the lowest point there in terms of energy levels, and they tend to be more stable than the random packs, which is something that is obvious, isn't it? When you compare a solid and a liquid, which one is more stable? Of course, the solid is more stable because the atoms are closely packed together and they're in one place. They don't easily move compared to a gas or a liquid. So there is another illustration also of the solids. Where I'm rushing too much, you please slow me down, okay? I may be tempted to rush because we have a lot to cover this evening. So we have the crystalline structures here. As you can see, there's a very perfect arrangement of the atoms in the crystalline structure. And on the right side, we have the amorphous structure. This reminds us so more or less of the Brownian motion, isn't it? From high school, usually would draw something like this to illustrate the Brownian motion. So in the amorphous structure, you see there's no exact arrangement. You see you have the atoms from a different elements there in red, they're just putting themselves wherever they can find space. Huh? And you have the blue ones there representing a different type of element. They're also just randomly spaced around. So under crystalline, what do we know? There's a long range order. The atoms are well arranged under crystalline. And examples of such structures are the metals. We looked at that also in our previous lecture. Won't go there. Under amorphous, there's a short range order. Atoms are arranged at random, and examples include glass. Okay, so we look at the liquid crystal here. First, you have this crystal, highly ordered, no translational freedom. As you are moving from a crystal to a liquid, then what's happening now? As you are, take for instance, you get your sugar, get your sugar and put it in a pan, and put that pan on the stove and switch on the stove. This is what you're going to observe. First, you have your sugar crystals, isn't it? Then as you're increasing your temperature, what begins to happen? You know, there's some melting you begin to see, isn't it? The structure, the crystals now begin to take up a smoother form. They're not really having corners at this point. As you keep heating, what's happening? Quickly letting go. Your atoms are no longer in this orderly manner of arrangement. And they keep scattering till finally, when you have your sugar now melted completely, it basically turns into a liquid. I'm sure we have all melted sugar before in our lives. We understand what happens when you melt crystals of that nature. So here you have increase as temperature increases, okay? Increasing temperature means decreasing order. As we are moving from crystal, liquid crystal, and finally a liquid. So the liquid crystal here is more or less what is known as the molten state, what we like to call the molten state, isn't it? Where a solution is partially solid and liquid. Then you have your liquid there finally, isn't it? Then you can burn it and turn it into tea, what we used to do back in the day. So you have your crystals there. This is the form, in case you've forgotten how the crystals look like. So there are different types of crystals that are found in nature. Here's an example. Precious stones usually take up the form of crystals also. Okay, so most people recognize this as a crystal, the beautiful shape, the color, we know the diamonds usually to be crystalline in nature. Then there's also the single crystal. This is an alloy, nickel alloy. Okay, it's just one crystal. By nature, it just doesn't form these polycrystals. It just has one crystal forming up. So there's a question here that is worth thinking about. Why do we need a single crystal for equipment operating at very high temperature? What do you think? Why do we need a single crystal for equipment operating at very high temperature? Anyone with an answer? All right, if you have no answer, you can still think about it. But again, go back to the illustration I gave you of sugar. Maybe that can help you understand, or maybe, understand better. All right, so we have the crystal structure. Like we say, this means the periodic arrangement of atoms or ions over large atomic distances. Okay, this leads to structure displaying. And then there's a long range order that is measurable and quantifiable. So these are basically other properties of crystal structures that are worth noting. So all metals, many ceramics, and some polymers exhibit this high bond energy and a more closely packed structure. All metals and many ceramics, not all ceramics, but many of them, and also just a fraction of polymers exhibit this high bond energy. So we come to amorphous materials. So these are less densely packed, low bond energies, structures that can be found in metals. It can be found in metals are observed in ceramic, glass, and many plastics. So this is an example here of a polycrystal under a microscope. So what does poly mean? We discussed this last time. Poly simply means many. So you have many crystals. You see, you have the structures here of crystals coming up and another arrangement a bit adjacent to this one. Okay, so you have all these different crystal structures coming in together. And then the borders between the different crystals, okay, are forming these patterns, these lines here. These are what we call the grain boundaries. We'll look at them later. So when you look at it even closer here to 5 microns, this is what you're going to see. So they're put in different colors just to help you distinguish the different crystals. So basically, this is how a typical polycrystal will look like. What else can we look at? So we say they're arranged in a periodic manner, and many materials have a crystal structure and are known as crystalline. Materials which do not have a crystal structure are called amorphous or non-crystalline. And then there's what is a term that we're going to use quite often. That is the term lattice. So what is a lattice? A lattice is an array of points in a structure which have identical surroundings. So the atoms or molecules are situated at these geometric points. So this is an array of points in a structure which have identical surroundings. Sometimes we sometimes interchange the word lattice with unit cell. Anyway, there's going to be an illustration in the next slide, so you look at it closely. And what's the concept behind here? The manner in which atoms, ions, or molecules are spatially arranged in a crystalline material is called a crystal structure. The manner in which your atoms, your ions, your molecules are spatially arranged in a crystalline material, that is known as a crystal structure. And some of the properties of crystalline solids depend on their structure. So in this case, when we're looking at, as we discussed further, we are going to imagine our atoms to be solid spheres, like we always have, isn't it? When you think of an atom, I think the first shape that comes to your mind is either a round thing, a round ball, or basically a solid sphere. And that is how we're going to imagine our atoms going forth. And in the atomic hard sphere model, the spheres are representing the nearest neighbor atoms. Well, these spheres, they touch one another, okay? Those atoms that are next, that have neighbors, the assumption is that they are touching one another. Then, like I said earlier, that sometimes the term lattice is used in the context of crystalline structure. And when used in this manner, it means a 3D array of points coinciding with atom positions. You see that also. In this part, okay, this is not 3D, so this is just in 2D now. Maybe we first start by understanding what we just talked about in 2D. So again, here I'll read the top. It says a lattice is an array of points in a structure which have identical surroundings. The atoms or molecules are situated at these geometric points. So you have a unit cell here, okay? So it's a square lattice. As you can see, this is basically what is the unit cell. Can also be a square lattice. So here, what's the parameter? 0.3 to 1 nanometers. Really, really small, 10 to the power -9 meters. So you have these X's here representing the position of atoms. As you can see here, one atom per lattice site. So this is known as a lattice site, okay? The corner here where there are two lattices joining together, where they meet the edges here, the corners, these are called lattice sites. So in this lattice site, we have how many atoms here? We have one atom. So this atom, as you can see, it's not in one box, isn't it? But it's an atom that is being shared by how many boxes? Anyone to tell us? How many boxes?
Oh,
4 boxes, isn't it? Yes, so you see one atom is being shared by this one, this one, this one, and this one. So now if it went in, okay, no, it's still in 2D, but just imagine that there was a similar arrangement on top of this one. So imagine that this is a mat, isn't it? A carpet with these boxes. Then when you put another carpet with exactly the same squares, what does it mean? It means these atoms will be shared by another 4, isn't it?
that's
Yes, so making it, meaning that this atom is shared by how many? 8 lattices, isn't it?
yes.
I need you to get this concept very well, because that's the one that we're going to use in our formulas. So meaning when you have imagined this as a carpet, then when you put another carpet on top of this one, it's the same, aligned in the same, with the same boxes aligned, exactly touching where these ones are touching. It means this one, this particular atom, each atom will be shared by 1, 2, 3, 4. Again, the ones that will come on top, 1, 2, 3, 4 boxes, meaning 8 boxes. So meaning each box has a share of what fraction of the atom, if there are 8 boxes and there's 1 atom. So meaning each box has what fraction of the atom? It means it has 1/8, isn't it? 1/8 fraction. Sure, where you look so surprised. Are we together? Or I repeat? Understood? Okay. So meaning each box shares 1/8 fraction of the atom. It has a share of 1/8 of the atom because there are 8 boxes sharing 1 atom. Okay, so sometimes you have two atoms, sorry, say lattice side. So you can see this lattice side here, this corner. There's an atom here and another atom here. So they are sharing 1 lattice side. As you can see here, it's known as a motif unit. Okay, this is a unit cell. This square here, or a lattice, as we like to call it, but it's also known as a unit cell, or simply UC. You see that also being abbreviated in that manner. Okay, so what is a unit cell? Describe the crystalline structure. It is often convenient to subdivide the structure into small repetitive entities called unit cells, okay? They're basically small repetitive entities of a crystalline structure, and we call them unit cells. So a unit cell is chosen to represent the symmetry of the crystal structure. Therefore, it is the basic structural unit or the building block of the crystal structure. The building block of the crystal structure and defines the crystal structure by virtue of its geometry and the atom positions within. Okay, so it's just it's a basic unit of a crystal structure. So one other thing worth noting is that crystals nucleate and grow. So nucleation, it means they just simply grow, okay? From outward, they grow outwardly. So they grow from the melt during solidification to form crystalline solids. An example is the process of smelting, isn't it? When you're trying to obtain iron from iron ore, you know the process, isn't it? The iron is placed into a smelter, a furnace, sorry, actually, for the furnace. And at a temperature of more than 1,300 degrees Celsius, that rock containing your iron, what happens to the iron? It begins to melt, isn't it? It melts and it's collected at the bottom in barrels, and then what happens? It solidifies. So during that solidification, you have crystals forming. Remember we say that all metals have crystalline structures. Yes, even iron, even aluminium, they all form crystals upon solidification. So you have your, basically there are your structures, and as this is high temperature to low temperature. So as your metal is moving from liquid to solid, it's solidifying, isn't it? So what happens first is bit by bit, you have the structures beginning to form there, isn't it? Then over time, what happens? More structures will form. You have the unit cells increasing. So your from these ones, just they start now growing outwardly. So we call that process nucleating. So your crystals there, your initial crystals begin to nucleate, okay? Form other crystals around them. Eventually they begin to close up the gaps between them. And eventually the gaps will be completely sealed, okay? And you just have the boundaries there, just indicating the borders between the different crystals that were coming together. Okay, and we come to this structure here, and these are known as grain boundaries, and these are called simply grains. This is just crystals with the same pattern are called grains. A group of crystals with the same pattern are called grains. So our meeting will be cutting after 40 minutes. So just simply use the same link to sign in. When I go off, just simply use the same link to sign in, and then we continue. So it will go off on its own. For now, we continue. Okay, so crystals or grains are typically 10 to 100 microns, but they can be small. They can be less than 1 micron, or they can be large to a centimeter. A micron, by the way, is much, much less than a centimeter. So you have your optical metallography here. This is a microscope trying to read what's showing here, isn't it? You have the boundaries there. They can be seen. You know, the size of 100 microns. This is what you begin to see. This is the annealed grains, and this is the code zone. You understand these also as we go. And then these are grains in an etched aluminum sheet. This is at 1 centimeter. So at 1 centimeter, you can actually see this in aluminum, in an etched aluminum sheet. Before it's polished and everything, you can actually see the grains very well. As you can see, this is what you're able to see. Okay, so unit form, just a reminder there with a definition. It's the smallest repetitive volume that contains the complete lattice pattern of a crystal. So there are different types of crystals. And there are actually 7 different types of crystal systems of varying symmetry. Okay. So these systems are built by the changing lattice parameters. So this is your unit cell in 3D. Okay. In 3D or in isometric, I don't know whichever way you're comfortable with, but we call this 3D. The 3D dimension of a unit cell. Okay, if we usually in 2D we're only seeing this face. Okay, but 3D allows us to see what's behind there and what's down there and what's at the other end behind it. The other corner is depicted here, which is our 0. Each time we're looking at crystals, we pick, this is always our initial point. So we have the A, B, C. So you have you have your sides here. Okay, so your x-axis is this one here. Sometimes they can be drawn differently, but I feel for us, for the sake of uniformity, we pick up this system, this pattern, where we have our x down here, our y on this side going to the right, okay, and our z going upwards. This is the system that we're going to pick. I'll repeat again, there are different depending on the textbook you're using. Your y can be where our x is, and so forth. But for us, we'll pick this system so that we all understand at the same time. Then we have our alpha angle here, and our beta angle here, and our gamma angle here. Please, it's not A, B, and Y, as my full-time students like to say. Not A, B, and Y, it's alpha, beta, and gamma. So these are the interactual angles. So alpha is here, beta is this side, and gamma is down here. All right, so these are the 3 types of lattices, the lattices that we have. So these are the 14 crystal lattices. So you have the simple cubic, body-centered cubic, space-centered cubic, The simple tetragonal. So as you can see, simple cubic only has atoms where? Only in the corners. And how many are they? Mr. Chewe. You can unmute your mic so that we hear you. How many atoms do you see in the simple cubic? How many dots?
1, 2, 3, 4, 5. 8.
8, isn't it?
8.
Because there are 8 corners, isn't
Yes,
it?
yes,
And how many sides does a cube have? Because all these
yes.
are cubes. How many sides does a cube have? 1,
6.
it has 6 sides, isn't it?
6.
Yes. If you used to play
Yes.
with the dice a lot, such games, you understand very well the sides. There are 6, isn't it?
Yeah.
The dice always has 6 sides. Yes.
Yes.
Because it's a cube. All right, so 6 sides, isn't it? For the simple cubic, the atoms are only in the, you can mute your mic. The atoms are only in the corners, making it 8. For the body-centered cubic, what does it mean? It means you have your 8, isn't it, in the corners, but then there's also another atom right in the center of the lattice, of the unit cell, okay, right in the center. That's why it's called body-centered cubic. It means there's an atom there in the center, in the body, inside the body of the lattice, okay. Then there's what is known as the face-centered cubic structure. In the face-centered cubic structure, you also have the 8 there, okay. You have the 8 there. However, on each face, you have an atom, okay. So we said there are 8 corners, isn't it? And there are 6 faces. So if every corner has an atom, plus the 6 faces, each face has an atom. How many atoms in total? And the face centered?
14.
14, yes. 8 plus 6 gives us 14 atoms. Then we have the simple tetragonal. What is the tetragon? Those that you remember, what properties does it have? What makes it different from a crystal? We don't remember? Okay, let's research. There's cube and there's tetragon, and there's this one, the orthorhombic, sorry. There's a simple orthorhombic body-centered, also it means there's an atom in the center. Then there's the base-centered orthorhombic, base-centered, so meaning on the bases, okay, at the bottom there's an atom, and at the top there's an atom, aside from the corners. So there's the corners are also how many atoms? 8, huh? Just like the cube. For the simple, the body-centered also there are 8 plus the middle one, meaning giving us 9 atoms. In the base-centered, it means there are 2 atoms, the top and the bottom, which are regarded as